In the 1960s, a quiet revolution took place that shifted our entire understanding of how the Earth works. Like many revolutions throughout history, it's not a single idea that came from a single person. But eventually, we pulled all that science together to create the theory of plate tectonics, which explains the structure and behavior of our home planet, how we got continents and oceans, mountains and valleys, volcanoes and earthquakes. It took many scientists many years to put together all the puzzle pieces to tell the story of how Earth's broken outer shell rises from the mantle and falls back in. Kind of like a dance of creative destruction and reconstruction that recycles Earth material between the crust and the mantle. And like Darwin's theory of evolution in biology and Einstein's attempts at a theory of relativity in physics, plate tectonics influences everything we know about Earth science. It's the grand unifying theory, and it was 4.5 billion years in the making. I'm Alize Carrere, and this is Crash Course Geography. Once we started getting a complete picture of the globe in the 16th century, we started speculating about the shape of the Earth's landmasses and if they once fit together like a jigsaw. Today, we refer to these landmasses as part of the lithosphere, the rocky outer part of the Earth that includes the crust and the uppermost part of the mantle. And we know it's broken into tectonic or lithospheric plates that each move independently of each other. But even though Africa and South America look like they fit together pretty neatly, all Earth's land being linked together long ago was a pretty radical theory. It would take over 300 years for astronomer and meteorologist Alfred Wegener to propose the idea again in 1912 and back it up with evidence. Using the spatial distribution of fossils, location of rock types, and trends of mountain ranges, among other evidence, he hypothesized that approximately 225 to 300 million years ago, the Earth's land was a single supercontinent called Pangaea, meaning all Earth in Greek. It broke apart in a process called continental drift and eventually led to the landmass distribution we have now, which was an outrageous proposal to the rest of the scientific community, or, geologists who were upset that a non-geologist was horning in on their turf. And to be fair, despite all his evidence, Wegener didn't have an explanation for the energy needed to break apart huge chunks of continents and plow them through the oceans. It wouldn't be until after the Second World War, when new evidence emerged from the depths of the oceans, that the idea of drifting continents was reactivated. In 1957, the first physiographic map showing the physical features of the Atlantic Ocean floor was published by two geologists, Bruce Heezen and Marie Tharp. Using a type of sonar device called a continuous echo sounder, Heezen collected bathymetric soundings, which are different depth measurements. This was the early 1950s, and Tharp couldn't go on research expeditions because she was a woman, so she converted the raw data into maps that revealed how the ocean would look if drained of water. The centerpiece of their map was a vast mid-Atlantic mountain spine crisscrossed by huge fracture lines, called the Mid-Atlantic Ridge. Heezen and Tharp focused first on the Atlantic, but it's just one of several mid-oceanic ridges that extend for over 60,000 kilometers across different oceans. Heezen and Tharp changed how we thought about the Earth, because the ocean floor wasn't just a flat, featureless plain like we'd assumed, but had mountains, valleys, and even deep trenches, which are the deepest feature on the planet. Then in 1960, Harry Hess, a geologist who had collected vast amounts of ocean data when he captained a ship equipped with an echo sounder during the Second World War, proposed that even more was happening on the seafloor. Magma spills out from the fracture lines of the mid-oceanic ridges. So Hess proposed that the seafloor was kind of like a giant conveyor belt. New seafloor was formed on either side of the ridges as magma flowed out and pushed away the old seafloor. And when it finally reached the distant trenches, the old ocean crust was cooled and dragged down into the mantle and recycled, which was another radical theory. Though geologist and oceanographer Robert Dietz published a similar idea he called the spreading seafloor theory in 1961. But the evidence was actually recorded in the seafloor itself and published a few years later in 1963 by geologists and geophysicists Fred Vine and Drummond Matthews. You see, the Earth's magnetic field reverses periodically, and this is recorded in rocks that contain iron as part of Earth's paleomagnetism. When magma cools and crystallizes, the alignment of the magnetic field is locked in place in the magnetic particles of the rocks. So each time the Earth's magnetic field flipped, the magma erupting at the mid-ocean ridges recorded the opposite polarity to the previous batch. The result is a magnetic barcode of black and white stripes that mark where polarity changed, arranged symmetrically around the ridge. That means Hess and Dietz were really onto something, and mid-oceanic ridges were built as magma on either side spilled out and spread laterally. This seafloor spreading pushes the seafloor away in both directions, and with it, the Earth's landmasses, which meant we finally had the evidence Wegener was missing in 1912 for how the Earth's landmasses were moving. Thanks to seafloor spreading, all of the Earth's seafloors are quite young, for rocks. In fact, determining the age of a basalt rock in the seafloor confirmed the matching patterns of magnetic histories. As for the crust being destroyed in the vast ocean trenches, it turns out that's exactly what happens too. In the late 50s and early 60s during the Cold War, when nuclear test bans were being negotiated between the USA and the USSR, a global seismic surveillance system was created to monitor underground blasts, which also happened to provide North American seismologists with observations of deep earthquakes more than 700 kilometers beneath ocean trenches. These observations were later used to visualize a thick slab of Pacific Ocean floor that was being pushed under the edge of a different slab of Earth's crust and consumed into the mantle in a process called subduction. Because the oceanic crust has a greater density than the continental crust, the thinner, denser oceanic plate dives beneath the lighter, thicker, and more buoyant continental crust. This forms a subduction zone, and what we see on the surface is a giant trench. So with ocean mapping, seafloor spreading, paleomagnetism, and crust subduction becoming confirmed pieces of scientific knowledge, the world was now on the brink of a revolution. The final piece of evidence needed to produce a grand unifying theory of earth science came from precise mathematical calculations combined with new computing power. With these techniques, geophysicists were able to calculate how the coastlines of the Americas, Africa, and Europe best fit together and predict how the tectonic plates moved. And with that, a revolution unfolded in earth science. Leading the charge was a bunch of mostly young, unknown scientists working in a handful of institutions in North America, Britain, and Europe. Fueled by the technology, money, and military in those places, they peered into the depths of the oceans and fundamentally changed the way we understand the Earth. Years of independent research and disparate discoveries finally described the structure of the Earth's surface and led to a map of the world divided into moving plates and created the theory of plate tectonics. Moving on average as fast as our fingernails grow, the 7 major plates and a scattering of microplates glide across the weaker, hot, plasticky section of the mantle called the asthenosphere. And we know now that where these plates meet are dynamic places where much of the planet's geological action happens, like earthquakes and volcanic activity. Like the area surrounding the basin of the Pacific Ocean is known as the Pacific Ring of Fire, or the Circum-Pacific Belt, because approximately 75% of all volcanoes are dotted around it, and 90% of earthquakes occur along its path. At the edges of the Ring of Fire, the plates come together in 3 different types of boundaries. On the eastern side, the seafloor spreads from the mid-ocean ridge called the East Pacific Rise that runs along the eastern edge of the Pacific Plate from near Antarctica all the way to North America. It's a divergent plate boundary, or place where plates are moving away from each other, with the Nazca Plate moving east and the Pacific Plate moving northwest. Along divergent plates, magma can well up and the seafloor regenerates and spreads. But farther south and west of South America, the Peru-Chile Trench marks the subduction zone where the denser oceanic Nazca Plate collides with and is pulled beneath the lighter continental South American plate, creating a convergent plate boundary. As the Nazca Plate is dragged down, enormous friction produces major earthquakes and hundreds of meters of sediments are carried down into the deep trenches. As the sediments melt, they turn into magma, which migrates up into the overriding plate. And where it reaches the surface, we get a volcano. Like the Andes, formed from plates colliding along a convergent plate boundary and have many volcanoes. Then circling north again, we find the San Andreas Fault along the west coast of North America. It lies on a transform boundary, where the North American plate, moving roughly southwest, is sliding horizontally past the Pacific Plate, moving northwest. Where the plates touch, they can get stuck and stress builds up as the rest of the plate continues to move. The stress causes the rocks to break, suddenly lurching the plates forward and causing earthquakes. So plates are moving away from each other, moving towards each other, and sliding past each other. But there's one more type of boundary that's not very common along the Ring of Fire. When continental crust converges with oceanic crust, the ocean crust usually gets subducted. But when 2 continental plates collide, neither plate is subducted. The collision compresses the crust, folding and pushing up huge mountain ranges, like the Himalayas. They sit where the Indian plate is converging with the Eurasian plate. So even as we speak, the structure of the Earth is changing as plates move all over the world. In the years following the revolution, the plate tectonics theory has been fine-tuned. And while we know a lot about how new ocean floor is created, how land masses form is also still being debated. We think continents grow from a nucleus of ancient and stable igneous and metamorphic rocks. And where these rocks are exposed at the surface is called a continental shield. And fragments of the crust that might originally have been offshore island arcs, undersea volcanoes, or islands like New Zealand or Madagascar are added to the main continent by collision. Today in 2021, we continue to explore plate tectonics. Plate motion is detected by satellites like the European Sentinel series, which record changes in Earth's surface down to the millimeter. The story of fragmented lithospheric plates moving around Earth's surface has had many twists and turns, but it's not over. Scientists want to know what caused the outer shell to crack apart in the first place, and how the recycling of the crust began. And they're even comparing Earth's plate tectonics with Venus, and asking why Earth has plate tectonics and Venus doesn't. As we learn more, crucial connections between deep Earth processes and the evolution of complex life are emerging. Continental collisions and mountain-building events may have supplied large pulses of nutrients to the biosphere during key moments of evolution, like during the Cambrian explosion of 500 million years ago. So that quiet plate tectonics revolution that changed our understanding of the Earth is kinda still happening. And we'll keep exploring these revelations next time when we look at how volcanic and tectonic activity shapes the landscapes we call home.